Hi, I'm Mira Kuntwala, and this is my lab on rope physics. So, for this lab, the objective was to observe the motion of a spring mass system that represented a situation similar to the extreme rope climber that we saw in one of our recent lecture videos. The way that we went about doing this is by analyzing a video in Tracker that Dr. Greco set up as a replica system similar to the extreme sport that we were trying to observe the motion of. Then, using VPython code, we created a predicted pattern of motion and energy graphs to compare the observed versus the predicted motion data to see if they matched up. And the result of this lab was that those two did match up, thus helping to prove that the energy principle is true and that energy is conserved. So, the fundamental principles that are very useful in this lab are the energy principle, which states that the change in energy is equal to the sum of all the different changes of energies. And in the case of this lab, those energies are the change in kinetic energy, the change in spring potential energy, and the change in gravitational potential energy. And of course, Newton's second law. For the code that we're using in this lab, there are a lot of components that we have to input by doing math by hand. Three of those that are very useful to us are the first one, which is a spring constant, which is K sub S. Next we have S, which is the change in length of the spring or the stretching or compressing of it. And lastly, LO, which is the relaxed length of the spring. To find the spring constant, we use the two formulas written below and isolate K sub S. To find S, we know that at static equilibrium, the force of the tension is equal to the force of the spring. So negative mg is equal to K sub S times S in this instant, and we can solve for S. Lastly, to find the relaxed length, we know that S is equal to the relaxed length minus the length of the stretch or compression, and that's how we can find our value for S. It's also very important that we know energy formulas that will be useful to us for the code, the first of which is the kinetic energy formula, and that states that 1/2 times the mass times the velocity squared equals the kinetic energy. Next is gravitational potential energy, which is just equal to mgh. And then lastly, spring potential energy, which is 1/2 times ks times s squared. So, once we input our video into Tracker, the first step that I took is setting the calibration stick here equal to 0.7 meters, and then setting our axes at the origin of the spring mass system with the x-axis pointing in the positive x direction and the y-axis pointing in the positive y direction up and negative y down. So then we assign point masses for every moment or frame of the motion, and you can see this here. So the spring mass is moving in an elliptical, and as you can see on the right here, a graph of this data is being plotted here. So now, highlighting all the x and y values, those were put into a CSV file that will help us to put this motion into VPython. So some of the major changes that we made in our code was right here when it says physgraph 4, we changed that because there are 4 different values that we're trying to graph as opposed to the one that was there before. Next, we changed the ball's mass to match the mass that was given to us, the original position, which these 2 points were from Tracker, the original velocity, which is 0, time, which is also 0, and changing the name of the file to match the CSV file that we created. Delta T stays the same, and then G is the gravitational constant. K sub S, LO, were both found by the formulas that we talked about earlier. L is ball's position minus the spring's position, L hat, which is the direction, and S, which is the stretching or compression of the spring. Now, these 3 formulas here match the formulas we just discussed that apply to the energies in our system. The while loop ends at the time of which the motion ends. And the values here for gravity and spring follow the formulas, and the total energy is the total force is equal to the spring force plus the gravitational force. And the ball's velocity and position are used by using Newton's second law to help us update these. Then we update the spring right here using L, L hat, and S formulas. Again here, the energy changes are formulas that we just discussed in the PowerPoint slides previously. Here's a still frame of the code once it was run and the energy graphs that it created. As you can see, the yellow line here represents the total energy, which should be equal to 0. Now, while the graph does oscillate a little bit at 0, my guess is that it's due to mainly a rounding error. Now to address the what does it mean questions. So for the first question, it's asking whether the energy principle is satisfied. And according to the graph that we just showed from ViewPython, the yellow line, which is representative of the total energy, lied right along the x-axis. Now this makes sense because the change in energy is equal to the work done on the system by the surroundings. And since all three forces and change in energies that we studied were in the system, there's nothing acting on the system. Therefore, the change in energy is 0. The second question, which asks about the oscillation between the x and y positions. Now, the oscillation in the time period and the change in x positions is much greater than changes in y positions, and this makes sense because our object has an elliptical motion, which is curved slightly downwards and means that the x positions are changing slower than the y positions.